Welcome everyone. So in this section we will understand what is exponentiation, how does exponentiation work and why do we need it, right? So first of all let us see what is exponentiation. So again it's a very simple mathematical formula funda, that is, if I multiply a b times, then I write it as a to the power b. This is normal exponentiation, right? So b is an exponent of a, and this is basically the number of times is b. Right now b is 4. Cool. So if I say a is 2 and b is 4, so I don't think I need to explain this, but still 2 to the power 4 will give me 16, right? So this is exponentiation. We all know this, that if I want to multiply a term b times, we get this, right? So that's not what this lecture is about. It is about how to find an optimal solution to finding the best complexity of exponentiation, right? If I want to find out the best complexity of exponentiation, that okay, find me a to the power b in very optimal time, what is the best you can do? The first approach is very simple, that okay, I can simply multiply a b times, right? So what's the total complexity of this? If I multiply a b times by using a for loop, it will be o of b, right? But that is not the complexity we want, right? We want it to be better than o of b, right? So here what we'll do is we will take help of binary functions, right? And we will call it binary exponentiation. Cool. This will be very handy, guys, believe me or not. In most of those problems in which we use mathematical expressions, in which, like, let's say there's a recurrence relation which is being solved, and that recurrence relation is being there's finally a formula that is coming up for a particular n, right? Let's say n square minus 2 n plus 1, right? Or n to the power some m minus something plus something and other things. So whenever there's a formula formed, generally we have some exponents, right? We have some uh, variables in that, we have some constants and some exponents. So how to solve those exponents in really very less time, right? So right now we are looking at binary exponentiation, and after this we'll be looking at modular exponentiation. Cool. So that will only require binary exponentiation, but still. Now let's move ahead with binary exponentiation, and let's take an example. So it's a very easy topic, guys, not a big deal, and a very short code for this too, right? So it won't take like more than 2 minutes, I guess. But yeah. So let's say I want to find out 2 to the power 10. Cool. So what we'll do is we'll take the exponent 10 and write it in binary numbers. We know exponent is this 10, if divided into binary, it is written as 1010, right? So if this 10 is written as 1010, it means 8 plus 2, right? So what does 8 plus 2 means? That yes, I divided this 10 into binary, right? So cool. So now let's see how does binary exponentiation work, right? So right now what I'll say is I'll take a, I'll take b, and I will take another term called resultant, right? So in resultant, what I'll do is I'll keep on multiplying a at some specific locations. So just say this, right? So initially what happens is a is equals to 2, b is equals to 10, and resultant is equals to 1, right? Because if I want to multiply something to resultant and I want some answers, so I should take 1 as the resultant value, not 0, because if I multiply anything with 0, it returns me 0. 0 is like a black hole, right? You do anything with it, it will just absorb that thing and make it 0. So yeah, so in the first step what we'll do is, okay, so right now I'll write b in binary form. Cool. So b is binary over here, right? So there are some steps, guys, that we need to follow. The first step is very simple, that check if b is last set bit, check if uh last bit of b is set, right? So guys, if the last bit of b is set, right now it is not set, then what we'll do is we'll simply say result, we'll simply multiply resultant into a, right? So I'm just not giving you a algorithm here, I'm just not giving you a dry run of 2 to the power 10. I'll also explain you like how did it come, right? So before moving on to that, I'll just simply write 2 to the power 10 can be written as 2 to the power 8 into 2 to the power 2, right? So this is the whole funda, guys, that we will simply divide two's powers and multiply them, right? If I multiply 2 to the power 2 into 2 to the power 8, this will give me 2 to the power 8 plus 2, which is 2 to the power 10, right? So this is the normal funda, guys, the main idea behind binary exponentiation, right? And how is that being done, that I'll simply show you over here, right? So cool, before moving on to the algorithm, let's take this cool example. So we have 1 0 1 0 here. What I'll do is 0 1 2 and 3, right? So if I take powers of 2, what I'll get is 2 to the power 0, 2 to the power 1, 2 to the power 2 and 2 to the power 3, right? So I have 1 2 4 8. I've just written 2's powers over here. So these are 2's powers, and this is binary of 10, and these are just indexes of my bits, set bits, right? Now what I need to do is simple. So here I'll get 2 to the power 1 initially, right? Right now my a is 2 to the power 1, so this will be a. Then 2 to the power 2, 2 to the power 4 and 2 to the power 8, right? So guys, the simple thing to notice is that if I have 1 as a set bit, then I'll simply include these two values into my resultant. I'll simply multiply these two values into my resultant, right? So resultant into 2 to the power 8 into 2 to the power 4 is equal to resultant, and this will become 2 to the power 2, right? This will become 2 to the power 10. Clear, guys? Not a big deal, right? So this is not 2, this is a. That's what we are gonna do, right? So for another example, let's say I want to find out 2 to the power 14. So it is 8 plus 6, 6 is 4 plus 2, right? So this is 14. So for this, how can I write 2 to the power 14 in binary form? It becomes simple: 2 to the power 8, 2 to the power 4 and 2 to the power 2. So I form these three terms. How do I form these three terms? Very easy. Initially I have 2, guys. If I square it, it becomes 2 square. If I square it, it becomes 2 to the power 4. If I square it, it becomes 2 to the power 8. If I square it, it becomes 2 to the power 16, to the power 32, to the power 64 and so on, right? So whatever a I'll have at that moment, after one iteration, what I'll say is a is equals to a into a, that is a square. Simple as that, right? So that's what we are going to do over here, that check last set bit of b is set or not. If it is set, what does it mean? If the last set bit is set, simply include that multiply a into resultant, right? So I'll simply multiply a into resultant, not a big deal, right? And if the bit is not set, no problem. What is the second step? No problem. If it is not set, simply right shift b, right? Because I'm always checking the last set bit. So if b is 1010 initially, in the next iteration b will be 0101. In the next iteration b will be 0010. Next iteration 0001, and the next iteration 0. I'm right shifting b, right? What does right shift mean? Just shift the bit rightwards. Cool. Because I want to check all these bits of b, right? And while I am like shifting b right times, so right shift b. And if I am right shifting b, so what is the third step? So at the same time I have to say a is equals to a square, right? I have to keep on multiplying a2, right, guys? So a will become 2 to the power 4 here, 2 to the power 8, 2 to the power 16, sorry, it will become 2 square, 2 to the power 4, 2 to the power 8 and 2 to the power 16, right? So guys, if the last set bit is set, then what I'll do is I'll simply multiply it into the resultant. What I'll multiply a into the resultant, right? Whatever the resultant value I have. So if I multiply a into the resultant, what I'll get is 2 square. Then again, let's move to the third step. This is the third step here. Is the last bit of b set? No. If it is not set, do nothing, right? So resultant is still 2 square, and then move to 2 8. 2 to the power 8. And what happens here is, if just check last set bit is set, yes it is set, then simply multiply a into resultant, so it becomes 2 to the power 2 into 2 to the power 8. And then finally what we have is b becomes 0, right guys? So if b becomes 0, what does it mean? That we don't have to carry on further calculations, because anything to the power 0 is 0, right? So I don't have to calculate anything else. So here I'll break. What is the resultant that we got? It is 2 to the power 10, right? So of course you can apply a for loop and check that if the bit is set, multiply it, if not, continue forward. Here I'll be using a while loop, because the code becomes really easy to code, right? So let us quickly do this part, right? After this we'll move on to modular exponentiation, guys, and that's also an interesting part and very easy part, right? So let's call this function power, right? So this returns me a to the power b. So what I have is, I take resultant initially, and resultant should be 1. So while b, so until y is greater than 0, what I'll do is simple, I'll check the last set bit. So if b and 1, that means the last bit of b is set. So if you're not clear with all this bit manipulation and or and other things, then simply watch out the number theory section. These are the basics, right? So what I'll say is resultant into equals to a. I'll simply multiply a into resultant. Otherwise, whether it be set or not, I'll simply say a is equals to a square. That means I'm multiplying a into a, and b slash equals to 2. That means I'm right shifting b, right? So you can do it this way also. B right shift 2 times, or you can divide it by, sorry, b right shift 1 times, or you can divide b by 2. So if I divide b by 2, it is right shift b 1 times, right? If I divide if I multiply b by 2, it becomes left shift b by 1, right? So these are small tricks that you should know. Finally what I'll do is I'll return the result, nothing more to do, right? So let's print this. Yeah, so let's take 2 and 10. So we got 1024, right? So if you want to check, if you want to print out all these things, you can like directly see out whatever stuff you want to and check how is it working, right? So if I do 2 to the power 20, it's very simple, I'll get a perfect answer, right? Because here we have used binary into work. So guys, why have we used binary into work? Because if I write b as in binary, and let's say b is approximately 10 to the power 18, right? So guys, if I multiply, if I like find out this term, cool, let me, if I say a into a to the power b, where b is approximately 10 to the power 18, then I cannot find out this value, right? It will be too huge. So for that I have modular exponentiation, do not worry about that. The second thing is that, okay, I do not have the the machinic capability of calculating this if b is 10 to the power 18, because it will take a lot of time, right? So in 1 second, for an like an average, in 1 second I can calculate 10 to the power 7 steps, right? So how many seconds will be required to calculate 10 to the power 18 iterations? It will be 10 to the power 11 seconds. I guess that is nearly equal to life of earth, right? That's too huge. So so what we'll do is we will simply convert this number into binary. So in binary, its length will be at most 64 of length 10 to the power 18, and in only 64 operations, we will simply find out a to the power b, where b is very huge. Cool guys, you can check this out. So this works in O of log b, right? Why? Because we are always dividing b by 2 in every step. So there will be a time when b will be 0. And how much time it will be 0? When the first set bit of b becomes the last set bit of b, and it goes away in b, right? So that's a very good complexity, guys. O of log b. So guys, this power function, it will be used in many problems and many statements, and it will also be used in many mathematical sections, right? It will also be used to calculate NCR. It will be used to calculate inverse of a number using mod, many things, right? So after this, guys, we'll discuss about a snippet, and that snippet will be very useful to all. right? So we'll discuss it, and this is just a part of it, right? In the next section we'll discuss about modular exponentiation, right? Not a five, it's a 5 minutes job. Cool. So thank you guys. Cool guys. So this was, in the previous video we discussed about binary exponentiation normal. Now let's discuss about modular exponentiation. So again, it's a binary exponentiation only, but under mod conditions. What is a mod, guys? What does mod means? That it's a remainder, right? So if I say 10 mod 7 is 3, right? So guys, generally what happens is that uh that the answers for some certain n for some certain problems are huge, right? If those answers are very huge, then what does compiler do? That of course those huge answers cannot be calculated very easily, because that will of course require a lot of space and lot of time to be calculated, lots of cost operations, right? So what does the problem setter do? What does they do? They say, okay, give me the answer by taking modulo with some prime number. Why modulo is with prime numbers? Because I'll leave it to you only. Find it out why we use modulos with prime numbers, right? Go over to cryptography section over the internet, just surf over it and check that why do we always consider prime numbers, because there are lots of theorems which are only applicable to prime numbers, right? So like Fermat's little theorem and other stuff. Cool. So what does he do is he says, okay, give me resultant mod prime, right, by taking a prime. So generally guys, this prime is 10 to the power 9 plus 7. You might have seen it somewhere, right? That okay, he says give me mod prime. So guys, we all know about modular arithmetic operations, like how to perform addition, subtraction, multiplication and division using mod. So that has already been discussed in the mathematics section, right? So here we will understand how to find out binary, how to like do this binary exponentiation under modulus, right? So let's say if I want to find out 2 to the power this, isn't it too huge? So let's say 2 to the power 100, right? So again guys, this value is too huge, right? Because 2 to the power 64 is like around 10 to the power 18, which can be stored in C++ with long int, right? But so this is around 10 to the power 19, right? So but 2 to the power 100 will be a huge value, right? Which we won't be able to store it. But still, if I want to calculate, if I want to find out what is 2 to the power 100, and under some modulus statements, right? He gave me 2 to the power 100 with some modulus. Let's take mod with some, let's call it an integer mod, right? So how will I do it using binary exponentiation? Very easy guys. That what so we all know that if I'm multiplying some a into b and I want to perform mod where a is less than modulus and b is less than modulus, then this becomes a mod. So this becomes uh a into b mod, right? So if I want to calculate this particular part, then it becomes like a mod into b mod, right, and wholes mod. So whenever I multiply two integers which are less than mod and I have to multiply and take mod, so I just multiply them and take them mod, right? So similarly guys, for addition also we do the same stuff, right? But that's not my point. What I want to explain to you is that how is binary exponentiation being done. If I write let's say I'm finding a into a into a 1 2 3 4 5 6 7 8 9 10 11 times. So how does binary exponentiation work? It will take this 1a, right? Then it will take this 2a's together, and then it will take this 8a's together. That is 2 to the power 8 into 2 to the power 2 into 2 to the power 1 will be equal to 2 to the power 11, right guys? So let's get back to the code. What happens here is I always multiply a into resultant, and then I say a is equals to a square. So what I want is I want all these values to be less than 10 to the power 9 plus 7, and I always want to keep them less than 10 to the power 9 plus 7. So how will I do that? Very simple guys, because as we can see there's only one multiplication operation happening here. That means if let's say resultant is around 10 to the power 9, right, and a is also around 10 to the power 9, both have 9 lengths, and if I multiply them, both of them will have 18 length. So that particular length of 18 can be stored in long integer, right? Similarly guys, this can also be stored in long integer, right? So after calculating both these values, what I'll do is I'll simply take mod. I'll just reduce their values less than 10 to the power 9 plus 7. I'll just take a mod. So firstly, let me save this code, binary, right? And now it's the new code. Yeah. So here what we'll do is we'll simply do a modular exponentiation, right? So for that, let's take a constant int mod. So why I'm taking a constant int mod, guys, because generally, so constant is not necessary. Yeah, this is not necessary. We can take int mod, right? So yeah, so I'm just taking it as a global variable, right? Because in power function it will be used, while calculating factorial mod p it will be used, right? So instead of passing it over here, just take it as a global variable. Because what happens, guys, if in a particular code, in a particular problem, if you want a result mod some prime number, so that prime number will not only be used in this power function but everywhere in the code, wherever you are doing an addition or a subtraction or a multiplication or a division. Just it's better to take mod rather than to pass it individually to all the methods. Cool. So I've taken resultant to be equal to 1. I don't have to take mod because it is already less than 10 to the power 9 plus 7. So guys, the problem here is that, okay, if I multiply resultant into a and both of them are of range 10 to the power 9, so, so this will go into the range of 10 to the power 18. So integer won't be able to store that, right? So for that I have already told you workaround, that is, let's define int as long int. Cool. So now guys, we have long integers over here and we don't have to worry about the other stuff. So after multiplying both of these values, what we'll do is we'll simply take mod, right? So let's take mod side by side. So resultant mod, and again for a also let's do the same, right? So why am I doing this? Because this ensures that a remains less than 10 to the power 9 plus 7 and resultant also remains less than 10 to the power 9 plus 7, so that whenever I do this multiplication and I take the square of a, both of them go at max 10 to the power 18, because this is 10 to the power, these are less than 10 to the power 9, and the 10 to the power 18 number can be stored in a long integer, right? So that's why guys they take 10 to the power 9 plus 7, right? Because if I multiply them, right, if I multiply two numbers of this particular value, then they get stored in a long integer. So that's what we want, right? And whenever I'm multiplying them, and again, like on the spot I'm taking mod, so I don't want their value to exceed this particular value, right? Because they are used in calculations. Again, so the 2 to the power 20 will be very easy, the same value, but let's say 2 to the power 200. So this will give me mod with this particular value, right? So this is not 2 to the power 20, it is 2 to the power 200 mod 10 to the power 9 plus 7 if I take remainders, right? And why are we taking remainders? To make our values in the limit that our language, our compiler can hold. Cool. So this was it about modular exponentiation. Not much changes required, only we just took mod side by side. Why we don't have to take mod by b, right, into b? Why? Because we are dividing it, we are not multiplying or adding it by something, right? It has to be in binary. Don't ever take mod into this, otherwise the value of b will change and then there will be some other binary, right? So thank you guys, see you in the next part. Welcome back guys. So here I have a very cool problem for you, and first of all I want you to go through this, that there are 10 types of people in the world, those who understand binary and those who don't. So is this 10, or you can convert this to binary, right? So yeah, now let's move on to the problem. So the problem is very nice and it will give you a deeper dive into what is actually binary exponentiation. So it's a divide and conquer approach, right? But we are actually using bit manipulation to code this part, right? So The problem is very simple. You are coding this in C++, so do not think of any other language because it will become very easy. So, so what you have is you have been given three integers, A, B and C. The fun fact is that all these three are less than equals to 10 to the power 15, right? And what you want to do is you want to find out A into B mod C, right? So you want to find out this A into B mod C. How do you do it? So just imagine yourself sitting in an interview and solve this problem. Just pause the video and try to do this. So of course guys, brute force won't work. So you can't just see out A into B mod C, right? Why brute force won't work? Because simple guys, because A is of 10 to the power 15 range, B is also of 10 to the power 15 range. So if you multiply them, even in like inside, or if you're just multiplying them, so this way this is actually exceeding my long int range. Even unsigned long int range is also being exceeded if you multiply these two values, because the range of the new number will go around 10 to the power 30, right, which cannot be stored in any format. It can be stored in string, right, but that will become again a heavier task to code it as strings, right? You have to do that pen and paper job again, right? So I'm not asking for a string solution, but a good one. So how do you do it, guys? So this won't work. We are very clear with this, because this is going above the limit of my long int, and it will give me a garbage value. So garbage value mod C will be another garbage value. Cool. So this is not working. The second is, some of you might be thinking the second approach, that is A mod C into B mod C mod C, right? So that's how we distribute mod inside whenever we are trying to find this. So again guys, the same reason. So let's say that A is equals to B is equals to 10 to the power 15, and C is equals to 10 to the power 15 minus 1, that is 9 14 times, right? Whatever. So if you take A mod C, okay, so I think I have just reversed the situation. Yeah, so let's say A is equals to B is equals to 10 to the power 15 minus 1, right, and C is 10 to the power 15. So if you take A mod C, then it will be A only, because C is greater than A. Similarly guys, B mod C will be B only, because it is greater than, because C is greater than B, right? So what does this problem statement converts into? What does it actually become? It becomes a normal statement, that is A into B mod C, where A and B are less than 10 to the power 15 and C is also less than 10 to the power 15. That means, what I mean to say is, this mod is unnecessary here in this case, right? Again, both A and B are of range 15, 10 to the power 15. Both of them are of this range. They cannot be multiplied by brute force. I just want you to uh if you're not like if you want hint, so this is a normal hint that you are watching this video under the topic of binary multiplication. So instead of exponentiation, we have multiplication, right? This nothing different. So it's like काफी relatable. It's like relatable. From this to this, you can easily relate. That is, in binary exponentiation, what happens? And here let's write binary multiplication. So binary exponentiation, what does it do is it calculates a to the power b, and this will calculate a into b. Mod m will be taken later, do not worry about that mods, right? Second thing is, in binary exponentiation, it is actually a multiplied b times, but in binary multiplication it is a plus a plus a plus a b times. In both, what we'll do is we'll simply divide or break b into binary, right, and the rest of the part will remain same, right? So here in like binary exponentiation, I was actually multiplying a by resultant, But in binary multiplication, I will simply add a to the resultant. Here I am saying a is equals to a square, but in binary multiplication, I will say a is equals to 2 into a, right? So what does I mean? That if I want to find out a into b, that is, let's take an example, 2 into 10, right? So how can this be written? This can be written as 2 into 4, sorry, 2 into 8 plus 2 into 2, right? Because I have divided 10 into binaries. Not a big deal, guys. Divide the next term into binary and finally do these multiplications and continuously take mod, right? So a very easy task, guys. So let's code it out. I don't think much explanation is needed here, right? So yeah, so if I want to, yeah, this is, let me save it. Have I saved it? Yeah, I've saved it. So let's multiply let's multiply a into b with some c, with some mod of c instead of this mod, right? And yeah, let's take this. Resultant is equals to 1, guys, not a big deal. So again, until I have b, then what I need to do is simple. If, so why I don't know why did I erase it. If b and 1, then resultant is equals to resultant plus a, not multiply this time. So a is equals to 2 into a, or instead we could have written as a plus equals to a and b slash equals to 2, right? So for now, let's take a very basic example. Let's say 2 to the power 10, and let's say the mod is very big integer 189 plus 7. Achha, okay, it's multiply. So okay, sorry, resultant will not be 1, it will be 0, because right now I'm adding things, not multiplying, right? Initially it is 0. Yeah, so I've got 20, and let's say 2 to the power 20. Right now the mod should not work because, so 2 into 20 is 40. Again, 20 into 20 will be 400. I hope you have understood this part. Now let's do the modulus part, guys. Again, the same thing, that resultant is equals to resultant plus a. So whenever resultant exceeds my mod limit, let's take mod. Similarly, a is equals to 2 into a, and it whenever it exceeds my mod limit, let's take mod by c. Cool. So why am I doing this? Why won't it exceed my long int range? Because very cool problem, guys, that I am just adding a to resultant, right? So resultant is becoming resultant plus a. So guys, both resultant and a are less than 10 to the power 15, because I am continuously taking mod. If even they exceed 10 to the 15, I am continuously taking mod, right? If I add both of them, then what will be their range? Around 10 to the power 16. In the worst case, if I add two integers of 10 to the power 15 range, in the worst case they can go to 10 to the power 16. So this 10 to the power 16 is easily storable in my data, in my long int. Easily storable, guys, because we are just adding two integers. And again, what's the second operation here? See, very easy. We're not multiplying anything, right? So this is 2 into a. Of course we are multiplying, but we can also write it as a plus equals to a, right? So again, what am I doing is I'm saying a is equals to a plus a. Again, I'm adding two integers of range 10 to the power 15, so their total range will be less than 10 to the power 16. And then when I'll take mod, they will again become less than 10 to the power 15. Why? Because c is less than 10 to the power 15. So while taking mod by c, they will again move back. So this is just to give you a brief idea about how does exponentiation, what is binary conversion of a number, how is this while loop actually working. So it's not about multiplication or only about exponentiation. This can be used in various places, guys. In the next topic you will see what is matrix exponentiation. So in that also we'll be using the same thing, right? So I just wanted to give you a very uh, diverse application of binary numbers, right? So it isn't like binary numbers are a very big thing, right? They are kind of gift to the humanity, because everything that we see is working in binary, right? Maybe in like 100 200 years everything works in quantums, which are not perfect binaries, but yes, right now this video is possible because of binary, right? And yeah, So see you in the next part, guys. Thank you. Cool, guys. So welcome to the tutorial for matrix exponentiation. So matrix exponentiation will come handy in various dynamic programming problems, and all those problems in which you will be solving some linear recurrence relations, right? So for example, I'll give you the very basic example and then we'll move on to various different examples, of course, right? So right now I have this small cat face here, and I'll help you prevent this cat face, right? So when we'll code matrix exponentiation, I will not pass 2D matrices, but we'll work on 2D matrices in methods, in different methods, right? So pointers are a nuisance. They might be, but we'll avoid them, right? So we'll avoid nuisances. Now let's understand how does matrix exponentiation work with an example, right? So let's take an example first. Let's say I want to find out the nth Fibonacci number. Nth Fibonacci number. So it's a very famous series, guys, Fibonacci number series, because it is being used in various places and there are some well-known facts about Fibonacci numbers. You can easily search those facts. So if I want to find out the nth Fibonacci number, so let me write first few terms of this series. It is 1, 1. The first term is 1, the second term is 1. Now the third term is equal, the third term follows this pattern, that f of n is equal to f of n minus 1 plus f of n minus 2. That means f of 3 will be equal to f of 2, that is 3 minus 1 plus 3 minus 2 is f of 1. So the next term is equal to the sum of previous two terms, right? So it is 2, 2 plus 1 is 3, 5, 8, 13, 21, 30, have I missed? No. So 13 plus 21 is 34, and then 34 and next is 34 and 21 is 5 and 5, 55, and so on, guys. So it's an infinite series, it is never ending series, and after a certain time it grows like exponentially, right? So you can easily see this particular series, right? So if I want to find out the nth Fibonacci number, and let's say n is less than equals to 10 to the power 6, so it becomes very easy for me. I can directly use dynamic programming, dynamic programming, right? And a very simple code, guys. We can easily do this, not a big deal. If still you have a problem using dynamic programming for finding just a Fibonacci number, just go watch a section on dynamic programming, and in that the first example will be of Fibonacci numbers in 1D DP, right? Not a big deal. So dynamic programming is not a big deal for Fibonacci numbers, very easy stuff. So what happens in dynamic programming is that you take an array of length 10 to the power 6, right? And what you do is you calculate the third term by using the first two terms, then you calculate the fourth term by using the second and third term, then you that means you take an array and you simply fill the first two terms, that dp1 is 1 and dp2 is also 1, and then dp3 you run a loop from 3 to n and say that dpi is equals to dpi minus 1 plus dpi minus 2, right? So this is a normal loop from 3 to n, right? And after the loop ends we have the nth number filled, so we have dpn after this ends. But guys, this is not the perfect solution that I want, because it is for less than equal to 10 to the power 6, right? So for lots of my friends got this problem as the interview problem, that like a follow-up problem. They said that now n is less than equals to 10 to the power 18. Now how do you calculate this particular Fibonacci number, guys? If n is so huge, you cannot apply this loop from 3 to n, because again we cannot have a 10 to the power 18 length of loop. It will take a huge time, right? So how do you solve this? How do you figure this out? Like what is the, and also guys, that number will be huge, of course, guys. This number will also be huge, that is Fibonacci of 10 to the power 5. It will also be huge. So generally whenever you face this problem, they will say that take mod. Just like take mod is actually a compensation, right? It's actually a drawback of our languages, of the computer systems we have now. It may be not after 100 or 200 years, but right now this is a drawback. That's why we take mod to like written in our limits, right? Okay, so how do you solve this problem when n is 10 to the power 18? So that's the main problem that we are going to discuss in this section, right? So here guys, what I'll do is I'll take three matrices and just show you an example, and everything will become all clear, right? So let's take three matrices. The first matrix that I'm taking is a normal matrix, and let's call it Fn matrix, Fn, capital Fn. So this Fn matrix is a 2 cross 1 matrix, and in this I will be storing Fn, which is the nth Fibonacci number, and f of n minus 1. Cool. Now what happens is I have a T matrix, let's call it T matrix, and I'll fill the values laterwards. So I want you to fill the values of this T matrix. I want you to find out the dimensions of this T matrix such that if I multiply T matrix to this Fn matrix, that is T into Fn, this matrix gives me Fn plus 1. That is, this into this equals this f of n plus 1. So wherever n, I'll just replace it by n plus 1. N plus 1 minus 1 is n. So what should be my T matrix over here, guys? Very easy, that this f of n plus 1 matrix is actually nothing but, how is f of n plus 1 written as? It is written as fn plus fn minus 1, right? The sum of previous two terms in Fibonacci series, and this is fn, right? So if I take two ones over here, so this one multiplies with this fn, and this one multiplies with this fn, this row multiplies with this column and gives me f of n plus 1, right? So secondly, in the second, what we have to do is, guys, I want fn to be here, so I can take it 1 0. If I multiply this row with this column, it gives me fn. Cool. So very easy, guys, not a big deal, that if I multiply T matrix with fn, it gives me fn plus 1, right? Now let's say this fn is equals to f of 2, right? So let's say T into f of 2, this will give me f of 3. Similarly, guys, T into f of 3 will give me f of 4. Similarly, T into f of 4 will give me f of 5, and so on, right? It will go on forever, right? So if I replace f4 in this equation by T into f3, then I can write it as this way: T into f3 is equals to f of 5. So let's say I'm just trying to find f5. So now let's replace f3 by using this equation. Here what I get is T into T into f of 2 is yeah, one more bracket, is equals to f of 5, right? So basically, guys, if I want to find out some f of n, and I know what is f of 2. What is f of 2? F of 2 is nothing but the f2 term and the f1 term, which is 1 1. The base cases, basically, right? Base cases. So yeah, okay. So what happens is, if I want to find out T of n, so this actually becomes T to the power n minus 2. Yes or no? So T to the power n minus 2 into f2 is equals to fn. So we know, guys, these all are matrices which are being multiplied. So multiply follows that property, right? Whatever it is, associated or commutative, in which a into b into c is equal to a into b into c, right? So I'm just applying that property over here, and simply I grouped all t's. I'm just simply multiplying all t's. I'm just finding T to the power n minus 2. What is T over here? T is a matrix 1 1 1 0. This is matrix T, right? So now what is the solution that I have come up to, that if I want to find out Fibonacci n, I simply have to find out T to the power n minus 2 and multiply it by f of 2, right? That will give me fn, which is fn and fn minus 1, and I'll just return the topmost value, that will be equal to fn, right? So how do I do this, guys? How do I find T to the power n minus 2? Again, we can use binary exponentiation here. Instead of multiplying T 1 by 1 here, I can directly find out t to the power n minus 2 by using binary exponentiation, because guys n minus 2 is an integer, right? I can simply say while this term simply what we'll do is we'll take a resultant matrix that will be one identity matrix, right? A resultant matrix will be an identity matrix, and in each step, right? So in each step what I'll do is simple, just as binary exponentiation we did, that resultant will be equal to resultant into a if the last bit is set, and so on, right? So basically just consider t, this t as another integer, right? So we know guys, as integers multiply, so do matrix multiply. As integers add up, so do matrices add up, right? So I'm just instead of doing a binary exponentiation of integer, I'm doing a binary exponentiation of matrix, that is called matrix exponentiation, right? So instead of integer multiplications and integer additions, we'll be having methods which will multiply matrices and add matrices. So those methods will not take a 2D array as an argument, because I'll be telling you a best way to code this out, right? And you won't be like having this face, whatever this cat has, right? I hope you got this, that instead of integers we just use matrices, multiply them, add them, whatever we do, and simply use them, right? So I think that's it. And so first of all guys, I want you to code it out yourself, right? Like write method, write functions. If you have understood this part, just do it do it yourself first, and then move on to the next video in which I'll code it out, right? So there are various examples. Let me give you another example. This was a very easy recurrence relation, and let me give you a tougher one. So if fn is equals to a of fn, this is a recursive relation, linear recurrence, right? So instead of capital F, let's have small f. So f of n is equals to a of f of n minus 1 plus b of f of n minus 2 plus c f of n minus 3 plus d. How do you solve this? So guys, whenever you will just face a recursive relation, a linear recursive relation, and you want to use matrix exponentiation, my first advice for you will be to make this vector, right? Make this vector, that is fn, and make this vector which is a fn plus 1. So take fn vector, like what things I have, to make the next what things, right? And then make the t vector accordingly, that if I multiply t to this, I'll get this, right? So let's solve this. Just pause the video if you don't want to solve it right now. Just pause the video, think about it, and then uh, deep dive into this. So here a b c are some uh, constants, right, that are being given to us. So as I said, first of all, we will have this fn matrix, and we will like manipulate, we'll like keep on changing what all we need, right? So here we have fn plus 1 matrix. So let's say I have fn here, fn minus 1 here, fn minus 2 here, and yeah. So here let's say I have fn plus 1, fn um fn only, and fn minus 1, because I'm replacing n by n plus 1, and let's say I have d here, right? Or instead of d, let's take 1. You'll come to know why am I doing this. So yeah, now let's make this 3 matrix, guys. So to make fn plus 1, what I want is, I want 1 1 1, that is 1 into f, sorry, not 1, sorry, my bad, not 1. I want a into fn, b into fn minus 1, c into fn minus 2, and d, which is equals to f of n plus 1, right? Now I want fn in the second place, right? So what is fn in the second place? It will be simple 1 0 0 0, because when I multiply the second row with this, I will get fn, then it is 0 1 0 0, then it is 0 0 1 0, right? So Yeah, so I get fn minus 1, but here guys what I want is I want 1 to be carried forward, right? I do not want fn minus 2 to come at this location, right? So the last row needs to be changed. What will I have in the last row? I want 1, right? So it will be 0 0 0 1. So this is my t matrix. If I multiply this t matrix to fn matrix, I'll get fn plus 1. Then again I'll multiply it by t, again I'll get fn plus 2, and then again and so on. If I want to find f of n, just find t to the power n and simply multiply it by f of 0, right? And you can easily solve this then. Cool guys, I hope you are able to cope up with this. And in the next video we will so this is another example of a reconciliation. You can have various examples, right? And now we will see an efficient way of coding this in the next tutorial. Cool, thank you guys. Hello everyone, welcome back to this tutorial for matrix exponentiation coding part. So in the last tutorial we went through matrix exponentiation and now we want to code it out, right? So basically we just have to the main part of it is to have t to the power n, right? And yeah, so so before that let me tell you some good problems. I think so it is seq. This is a problem code on spoj. You can try this problem after this particular tutorial, and there is another spp, right? You can also, this is also on spoj. So solve these two problems after this and get your hands on matrix exponentiation. Cool. So firstly, so here we are, normal code. I've just taken int as long int because we'll be using mod again and again, because guys, very easy thing to notice that if I want to find out Fibonacci number of that bigger heights of that term, f of 10 to the power 18, right? So its value will be huge. I can't even imagine that huge, right? So what I'll do is I'll just take some mod here. Let's take it 189 plus 7. Cool. And let's find out the Fibonacci numbers. So what in the int main, let's say I have n and let's call it initially 5, right? So I want to find out what is the fifth Fibonacci number, right? So I'll just see out and I'll write a function, a method which will give me the nth Fibonacci number, right? So int fib and n will come over here, right? The nth Fibonacci number. Cool. So how do I code this? How do I make a matrix, right? So as I said guys, I'll be using a very special method which is a structure. So in structures we don't have to, we won't be worried about passing on different 2D arrays and other stuff here, right? So what I'll do is very simple. Firstly I'll just take a matrix. So instead of whole matrix, let's take m and let's give it a constant size. Cool. So constant size is 2 initially, right? Because for coding this part, that is Fibonacci part, right? We need 2 cross 2 matrices, and this is a 2 cross 1 matrix. So here you will realize one thing, that we don't need fn matrix. We don't need fn plus 1 matrix. We just need t matrix, and we'll find t to the power n minus 2. And when I have t to the power n minus 2, after this I just need to multiply that by 1 1. What does this mean? That if I take just first two terms and add them of t, that will be equal to, if I multiply the first row with 1 1 and get fn term, right? So I'm not like coding fn matrix and fn plus matrix because we don't need it. We just want t matrix and its power, right? So here I'll just take a structure matrix. So guys, you will easily see that why is it being so useful to us, why taking this structure is being very useful to us, right? So after this let's write a constructor matrix, and what it will do is it will just simply set this to 0, right? It will set all the terms to 0. Cool. After this let's write a method which will convert a matrix to an identity form. What is an identity matrix? It is 1 1 1 on the diagonals. So let's write a function called identity. So we need this identity. I have already explained this to you. Why do we need identity? Because instead of resultant, the resultant in multiplication was 1, in addition is 0, right? So it is an identity element. So in matrix it should be an identity matrix, right? So from I will go from 0 to size, and what I'll do here is m of size is equal to 1. I'll just in the diagonally I will put all ones. So this is an identity matrix, right? And now let's code the last part of this structure matrix, and the most um, important part, that is I want to multiply two matrices, right? So how do I multiply two matrices here? So if you have not heard about what do we call it, operator overloading, just go and check it out. It's a very very nice term, guys, like how to overload an operator, right? So I'll be defining this, that if I use a multiplication anywhere, then this particular function will be called. So this is called an operator overloading, right? I'll simply pass a matrix A to it, right? And what I'll do is I'll simply now nothing. If I say matrix, okay, let me give you an example. If I say matrix R, I just taken a matrix R, and I say if R is equals to R into, let's say, another matrix Q, R into Q, that means for this matrix R, this operator is defined, that is a multiplication operator after this. So this Q matrix will be passed as an argument to the function of R, right? That means R's method will be called, where A will be passed as a matrix, a different matrix as an argument. Now what I need to do is I need to multiply these two matrices, right? That means A has been passed to the argument, to the method as an argument, and I have to just multiply them. I don't have to do much part here now, right? So what I'll simply say, I'll just take a matrix, let's call it resultant. Cool. So guys, how do I multiply two matrices into a third matrix? If this is a matrix A, this is a matrix B, so I get a C matrix because both these matrices are of 2 cross 2. 2 cross 2, 2 cross 2 will give me 2 cross 2, right? If I A, B, C, D, D, E, F, G, so what is this term? It is equals to the first row multiplied by first column, right? So matrix multiplication is actually, and so this will be actually size cube algorithm, right? Because we'll be using triple for loops here. Why triple for loops? Because to fill one location of this matrix, to fill one location of this matrix, I need to go for the rows and for all the columns of both the matrices. So it's into 3, right? So let's do this then. So let's go from I0 to size, right? And then let's go from J0 to, sorry, size. So I'm just not doing anything here, not a big deal. I'm not doing a big deal over here, right? It's a very simple thing. I'm just multiplying two matrices. The first matrix is this, that is my R matrix, that this I've already explained. Second matrix which I'm passing to it as an argument, and the third matrix is resulted in, which I'm storing, right? So this is the matrix that I will return. So for all these locations of ij, that means for all this resultant ij, what I need to do is I need to simply have one more variable called k, right? And what will this k variable do? Simple. So for resultant ij, it will be plus equals to uh, m I k. That means k is going that means I is constant for the first matrix. For this m matrix, the I is constant and k is going one by one ahead for all the columns. And for the second matrix, what I'll do is simple. It will be equal to a dot m, that means A's matrix, right? A dot m kj, right? For the second matrix, the column is constant and we are simply moving down the row. It's just a normal multiplication and addition. And after this, what we need to do is simple. Resultant ij mod, we'll just take mod by 10 to the power 9 plus 7 so that the values doesn't exceed our limits. And finally I'll return the resultant matrix, which will be stored in R. Cool. So this is a normal matrix multiplication, guys. Normal matrix multiplication. You can easily see, guys, it has become so easy right now. If you would be writing different methods and providing 2D arguments to it, it won't take those arguments because they cannot be passed. So just told you a very easy method. Now you will easily see the similarity between the binary exponentiation and matrix exponentiation, right? Now you will see it. So initially what I'll do is I'll just take a resultant matrix, and what should be resultant matrix be? It should be uh identity matrix, guys. Resultant matrix should be identity, because if I have to multiply other matrices to it. Now guys, let's take the matrix called T that we have defined over here, right? Where is T matrix? Yeah, so I just have to, initially all are zeros, so T dot M, so at 0 0 I have 1, T dot M at 0 1 I have 1, and T dot M 1 0 I have 1, right? So at these three locations I have 1 in this matrix, you can easily see. Cool. So I just filled the T matrix, and now what is the need? The need is very simple, that if I want to find out nth Fibonacci number, I have to find out T to the power n minus 2, right? We have already discussed this part, why n minus 2 is needed, because I have to multiply it by f of 2. Let's find out T to the power n minus 2, right? So let's subtract n, and right, so before this guys, let's make a case. If n is less than equal to 2, then what we'll do is we'll simply return 1. Cool. Otherwise we'll simply subtract n by 2 and do the normal exponentiation here, right? While n, if n and 1, that means if it's an odd number, resultant is equals to resultant into t, right? And t is equals to t into t, that is t square, the normal thing that we did, and n slash equals to 2. So guys, you can easily see it has become so easy if I use the normal operator overloading, if I define a structure matrix. Isn't it very easy, guys? If you have coded this out, if you have tried this code, and just compare your code with my code, right, and you will realize the differences. After performing this while loop, what I'll have is I'll have the proper resultant that I want, right? I'll get t to the power n minus 2 in resultant, where resultant is 2 cross 2, right? So I just have to add the first two terms and return them, right? So what I'll return is I'll simply return resultant dot m 0 0 plus resultant dot m 0 1, right? And also I have to take mod. So guys, never forget mod. So yeah, okay, sorry, not I, it will be I, not size. So yeah, just let me check for some. So it is not resultant, it is resultant dot m, my bad. Resultant is a structure. Another error, right? So no error. So what is Fibonacci of 5? It is 5 as in the output. Let's check. Yeah, the fifth term is 5. So let's check for the sixth term, then we'll discuss the complexity. 8. Great. 10th term, so 1 2 3 4 5 6 7 8 9 10 55. Great, it's working perfectly, right? So this is the normal exponentiation part we have discussed. This is the matrix, right? And yeah, so now it's the time to discuss the complexity, guys. So what is the complexity of this loop? It is log of n, right? So this is log of n, right? O of log of n. And in this, what is happening? There's a matrix multiplication functions being called twice. So what is the time that a matrix is taking to be multiplied? It is size into size into size, that is size cube. What is size here? 2, right? So it is basically 2 cube, which is 8 into log of n, right? So isn't it so funny, right? So that it is, yeah, let me write it. It is size cube into O of log n, right? If n is like 10 to the power 18, it becomes 64 into 8. That's not a complexity, right? It's nothing, not even in 3 digits, right? So yeah, sorry, it's not even in 4 digits, it's just less than 1000. So that's the beauty of matrix exponentiation, guys. Cool. I've given you various examples of exponentiation and binary exponentiation, how they can be done, how they can be coded out, right? So this is the complexity. So here we cannot ignore size, because for this example here size value is 4, so it will be 4 cube into log of n, right? So this size cannot be ignored. And of course guys, after this I just move on to Spoj and check out these problems: SEQ, SPP, and there's another problem said it's called SPP2, because SPP recursive sequence, something like that. And then there's another thing, it is Fibosum on Spoj. Try that too if you wish to. Cool. I hope this code is very clear to you guys, and the complexity of it is also very clear to you guys. So that's it. See you in the next part. Thank you. Hello everyone. Let's solve this problem. Fibosum from Spoj. So it's very easy. The problem statement: the Fibonacci sequence is defined by the following relation: f0, f1, their values, and fn is fn minus 1 plus fn minus 2. We all know this. So your task is very simple. Given two non-negative integers n and m, you have to calculate the sum fn plus 1 till fm. Basically, you have to find out the sum of the series of Fibonacci numbers from fn to fm, right? And of course, mod is there. We know about mod, right? So this is the input t lines, and after all these t lines, we'll have this 0, 3, 3, 5, and all these things, right? So how to approach this problem? We have already seen, right, how to find out Fibonacci numbers using matrix exponentiation. So there are two approaches for this problem. The first one, actually both uses the matrix exponentiation, but there are two different ways of using it. The first one is to figure out a recurrence relation, right, of the sum. As we saw, right, we were making the T matrix. So in the T matrix we had many things. So similarly we can take sum, like sum of sum till n, Sn. Let me name that term. It's called Sn. Let's call it Sn. What is Sn? Sn is sum till nth Fibonacci number, right? Basically it is f0 plus f1 plus f2 till fn, right? And then Sm will be similar thing till fm, and if we subtract Sm minus Sn, or instead let's minus Sn minus 1, then we can simply get what we want, which is sum from m till n, right guys? I hope we all know this, because it's prefix sums, right? So sum for a range is total sum minus the previous sum. We'll remove it and we'll get this. I hope this is very clear, right? But then how to figure out Sn? So you can make a T matrix in which you can add Sn, and then see how does that you can make an Fn matrix in which you can add this Sn, right? We can have a third variable, that is, and finally you can have a the T matrix accordingly, right? That's one of the approach. I'll discuss that as well. But before moving to that approach, I want to discuss a very nice approach. It's based on the property of Fibonacci numbers, and we'll derive that property, right? So we say that fn is equals to f n minus 1 plus f n minus 2. So let's see what fn minus 2 here is, right? So fn minus 2 is equals to fn minus fn minus 1. I hope you agree on this point, right? So cool. So what will be fn minus 3 here? It will be nothing but fn minus 1 minus fn minus 2, right? I hope we are on the same page over here, and so on till, let's say, f0. So what is f0? Okay, let me write one more and then we'll do so on till f0. So it is fn minus 4 is equals to fn minus 3 minus fn minus 2, right? So n minus 2 n minus 3 n minus 2. Am I doing something wrong here? So fn minus 2 is fn minus 1. Okay, so fn minus 3 is fn minus 1 minus fn minus 2, right? Fn minus 4 is equals to fn minus 3. Okay, so I think this 2 and 3 should be replaced, right? And so on till f0. So what is f0? F0 is nothing but f of let's put 0 in this n. Let's put n equals to 2 here, right? So it will give me f of 0, and this will be f of 2 minus f of 1. I hope this is fine, right? Now guys, what if I add the LHS and the RHS, right? Let's add these values. So if I add these values, this is nothing but f0 plus f1 plus so on till fn minus 2, right? And what is on the LHS? On the RHS, the right hand side, I can easily see that this cancels out this. Similarly, this cancels out this, right? Because minus plus, they all will cancel out each other. And in the end, f2 will also get cancelled out because of some values over here. Finally, what we'll get? We'll get is equals to fn minus f1, right? So what I can see here is that s till n minus 2, right? Because it is starting from 0 and going till n minus 2 is equal to fn minus 1. f1 is 1, right? Fibonacci number of 1. So if I want, let's replace n by n by n. Let's replace n by n plus 2. So what I'll get? I'll get Sn is equals to f of n plus 2 minus 1. A very simple recurrence relation, guys. So if I want to find out Sm minus Sn, which is equal to, sorry, yeah, I want to find out the sum from m to n, right? So fm to n, this is what Sm minus, okay, let me not add the brackets, minus Sn minus 1, which will be, what is Sm according to this equation? It is f of m plus 2 minus 1 minus what will be Sn minus 1 according to this relation? It will be f of n plus 1 minus 1, right? Because I here I have n minus 1, here I'll replace n by n minus 1, so this n plus 2 will become n plus 1. Cool, let's subtract this cancels out this. What I have got? Fm plus 2 minus f n plus 1, right? So this is the final answer, and we all know how to find out the Fibonacci numbers, right? So we can easily find out fm by plus 2, we can easily find out fn plus 1, we can subtract them, add mod, take mod, because that modular properties are important, don't forget them, right? Because here in Spoj the answer is required after taking mod. So subtract them, add mod, and then take mod. I hope this is very fine, right? So you can easily code it now because there's nothing left, and we have already coded how to find out the Fibonacci number. Cool. So thank you everyone. Let's see you in the next part, in which we'll be using matrix exponentiation to figure out this solution. Cool. Hi all. So let's see the second approach, the other alternative approach of matrix exponentiation only. So if you are not able to figure out this one, which is also a nice approach, it's just based on the property of Fibonacci numbers, but yes, let's say it's not Fibonacci number, it's some other reason we want to find the sum, right? So let's see an example of how to do it. So firstly, I always started by writing some f metric, right? So let's say there's an fn metric, and this is let's say it has some till nth term. It has a Fibonacci number n because sum till n will require Fibonacci number n, and it will also require Fibonacci numbers n minus 1, right? Now what is the next metric that we can have? So if I multiply a t metric into this fn metric, I should get an fn plus 1 metric. So just replacing n by n plus 1, what should I get? Sn plus 1, fn plus 1, fn minus 1, right? So this was, sorry, yeah, this should be f n, not fn minus 1. So I'm replacing n by n plus 1, right? So now we can easily, let's make a t metric, which is very easy now because I have to use these three things to make Sn plus 1. So what is Sn plus 1? Can I write it as Sn plus Fn plus 1? Sum till n plus 1th term, right? Which is sum till nth term plus Fn plus 1. So how will this will be? It is very easy. Fn plus 1 is equals to Fn plus Fn minus 1, right? So basically it is the sum of all three, right? And the next term is Fn plus 1. So what is Fn plus 1? It is Fn plus Fn minus 1, right? Which is nothing but sum of both the lower terms. And the last one is Fn. I want to just find out Fn, which is just this cross diagonal, right? So this is the T matrix that's prepared for me for this particular F matrix, and this is Fn plus 1 matrix, right guys? So yeah, let me just quickly share an example that why it will work. So the matrix is 1 1 1 0 1 1 0 1 0, right? So let's say this matrix is the base case. Let's make a base case. So we have n minus 1 here, right? So let's make the base case. Let's replace n by 1. Cool. So this becomes f1, which is sum till one term is 1 because fn is 1 and fn minus 1 is 0. Cool guys. So what will be the multiplication of these two matrices? So it will be 1 plus 1 2, and the next will be 1 here only, and the last one will be 0. uh I hope, okay, the last one will not be 0, it will be this 1 into this one, so it will be 1, right? So this is the fn plus 1, which is f2 matrix, and this contains s2 sum till two terms of Fibonacci, right? Which is Fibonacci 0 plus Fibonacci 1 plus Fibonacci 2, which is 0 plus 1 plus 1, which is 2. I hope you got this. And again, if you multiply the T matrix with f2, let's say if I multiply T matrix with f2, what I'll get? I'll get f3. You can try this. Cool. So let's code it out quickly, and yeah, so this is just some previous code, and let me just remove this. I haven't changed anything over here in the matrix structure, and I just, yeah, so this is the function fibosum. Will pass n to it, and it will give me the sum of the nth term. Cool guys. So yeah, let me yeah, so let's see out fibosum, and we want to find out sum till mth term minus fibosum till n minus 1 term, right? So here we can see that n can also be 0. That means n minus 1 can also be negative, which is minus 1, right? So let's write some base cases, which is very simple. If n is minus 1, return 0, right? If n is 0, so what is the sum of Fibonacci 0? It is also 0. And if n is 1, then let's return 1. So let's return these three values. Now we know that n is greater than equal to 2, right? So here let me write it that n is greater than equal to 2, right? Now we have a resultant matrix that we used to have. This is the T matrix that I have to make. So the T matrix is 1 1 1 in the first row. So T dot m 0 0 is equals to T dot m 0 1 is equals to T dot m 0 2 is equals to 1. So fill the first row with 1, and also you can see that the size is 3 now. That means all the matrices here will be of 3 cross 3, right? I hope don't get confused here, right? So you can increase or decrease the size as you want to. And the second row is zeros on the second part. So let me quickly remove this. So T01 and 02 is 1, and the third one we have it in the just the middle part. So let me remove this, and let me also remove this, right? So as we can see, we have this 0 0, otherwise everyone will be we have these ones and everything else will be 0. Now this is the base case, right? So in the base case I can yeah, so n is greater than equal to 2 now. So basically if I let's say if I pass n equals to 2 here, what will happen? It won't go here. Cool. uh it this will fill. Now let's say n is equals to 2, so this while loop will go 2 times, right? It will meaning it will try to find square of it, right? Basically it will find t square into whatever the base case I am multiplying, right? So the base case here is nothing but this, which is 1 1 0, which is f1, right? So I'm trying to multiply this f1 with t square, but that should not happen, right? Because t square into f1 will give me f3 and will not give f2, right? So if I'm passing n as 2 here, let me subtract n by 1, n minus equals to 1, right? Why am I subtracting n by 1 here? Because if n is being passed as 2, I just want to find out t to raise to the power n minus 1 and not t raised to the power n, because t raised to the power n minus 1 into the base case is giving f2 and not f1. I hope you got this. So this is we are just subtracting 1 because let me also quickly write this, because t square f1 is t3, sorry, f3, which will give sum till third, right? Similarly, t cube f1 is f4, right? So basically, if n is 3, then we are getting fourth answer, but we want third answer, right? So I'm just subtracting n by 1 so that we can get the third answer. I hope that's fine. Now after this, we have found out that there is this t matrix is we have found out the t raised to the power n minus 1, and after I have found out the t raised to the power n minus 1, what I can do is uh, I just have to multiply the first row with the first column of the f, because I just want Sn term, right? Here I just want the Sn term, right? So I'll just multiply the first row with this column, which is 1 1 0. So indirectly what will happen, this will get multiplied by this will get multiplied by this, right? And this will get multiplied by this. So basically fn minus 1 is 0 because of the base case. Okay, let me write here. Basically it is t raised to the power something, let me call it k, into the base case. What was the base case? 1 1 0. So we know the first row will get multiplied by these terms, so let me write first row as abc, right? So it will be a into 1 plus b into 1 plus c into 0. So we are not considering c. What we'll do is we'll say a into 1 plus b into 1, right? Which is nothing but resultant dot m00 a and resultant dot m01, which is b. So I'm not taking the third value, because if I take the third value, I'll say this, let's say 0 1 2, I have to multiply it by 0, right? The base, in the base case, we saw that it's 0, the fn metric, so we'll not multiply this. And finally we'll take mod and return the values. I hope this works. Let me build this quickly. Okay. Okay, it's 2 0 0, right? So let me quickly go over this again. I don't think so there should be an error. This is the t metric. The t metric is 0 1 1, okay, 0 1 2 and okay, and 0 1. Okay, sorry, this is the first row, right? So in the first row it should be 1 1, and in the second row it should be 2 1. My bad. Right, now we are seeing good numbers. My bad, sorry guys. Because in the first row it should be 1, right? I just copy pasted it. Always happens with me whenever I copy paste things. So here what we have 4 10 and yeah, so it will still not work. Why? Because here I am subtracting, right? Let's say the numbers are huge. If I subtract them, they will not give me the right number because of the modulus properties. So what I'll simply do is I'll add mod, and then I'll again take mod, right? And then this should give me the perfect answers. As these numbers were small, so it was giving me right answer. But just remember, this is the modulus property. Don't ever forget this. If you subtract, so there was a time when I was giving some long challenge, and it took me 2 days to realize this, because at that time I was so new to programming. No one was going to tell this part to me, and it took 2 days to figure out that a minus b plus mod, uh, a minus b. If I want to take mod, it should be a minus b plus mod then whole mod, right? So yeah, and we can simply submit this code as well on this podge and to the, yeah, let me submit it also. I'll strongly suggest that you all try it once before and then submit it. Cool. So thank you everyone, see you in the next part.